Hi everybody. In this video I'm going to do an example problem involving work, kinetic energy, and the work-kinetic energy theorem. Imagine we have a 100 kilogram crate initially at rest at point A on a horizontal frictionless surface. Imagine there's an applied force of magnitude 200 newtons and 60 degrees above the horizontal. Let's imagine that for the duration of this problem, this force remains constant. That means constant magnitude, constant direction. Let's imagine there are no other applied forces to the crate, so that the only forces acting on the crate are this applied force shown here, the downward force of gravity, and the force that the floor exerts upward on the crate, the so-called normal force. Given this information, here's what we're asked to find. For the first 2 meters of travel, as this object goes from point A to point B, we're asked to figure out the work done by the 200 Newton force, which I'm going to call W200. We're asked to figure out the work done by the gravitational force and the normal force, W-grav and Wn respectively, as this object goes through the 2 meter displacement. We're also asked to calculate the net force. And then finally, we're asked to figure out the speed of this crate at point B, which I'm going to call V sub B. That's the speed after it's gone 2 meters. We're going to do this 2 different ways. First, using the work-kinetic energy theorem. Second, by finding the net force, calculating the acceleration, and figuring out how fast that acceleration would have this object going after a horizontal displacement of 2 meters. And then at the very end, we're going to explore a what-if scenario. What if, in addition to this 200 Newton pulling force, 60 degrees above the horizontal, we also have a 100 Newton pulling force that's to the left and above the horizontal by 30 degrees. We'll explore what that means, what impact that has on the speed at point B. All right, let's get started. In the case of a constant force and a straight line displacement, the general definition of work simplifies to this expression here, where the work is then the dot product of the constant force vector and the straight line displacement vector. So I can write that right here. And since we're trying to find the work done by this 200 Newton force over this 2 meter displacement, this force F will be the 200 Newton force 60 degrees above the horizontal, and the displacement delta R is this 2 meter displacement to the right. So to evaluate this dot product, we can use the general recipe for the dot product. So we need to take the magnitude of the first vector, that's the force vector, has a magnitude of 200 newtons. The magnitude of the second vector, delta R, that has a magnitude of 2 meters. And then I need the cosine of the angle between those vectors. The force vector makes a 60-degree angle above the horizontal, but the displacement is horizontal, so we have a 60-degree angle between the force vector and the displacement vector, the 2 vectors in our dot product. So I need cosine of 60 degrees. Now, cosine of 60 degrees is a half. 1/2 times 2 times 200 is 200. So we have 200 newtons times meters, which gives us joules. So the work done by the 200 Newton magnitude pulling force, direction 60 degrees above the horizontal, over this 2 meter to the right displacement is 200 joules. All right, let's find the work done by the gravitational force and the normal force, so W-grav and Wn respectively. To do that, let's think about this dot product. The dot product of 2 vectors will be 0 if there's a 90-degree angle between those vectors, because cosine of 90 degrees is 0. So the dot product of any 2 vectors that are perpendicular is 0. All right, well, the gravitational force is straight downward. That's perpendicular to the displacement. The gravitational force is constant. The displacement's a straight line, so we can use this dot product again for the work, but we're taking a dot product of 2 vectors that are perpendicular to each other. So the work done by the gravitational force is 0. Likewise, the normal force that the floor exerts on the crate is straight upward. That force will be constant. We have a straight line displacement. So again, we can use this special case formula for work done by a constant force and a straight line displacement. The dot product of the normal force vector and the horizontal displacement vector will be 0 because there's a 90-degree angle between them. So the work done by the gravitational force and the normal force are both 0. So we've got 200 joules plus 0 plus 0 gives me a grand total of 200 joules. All right, So now we can try and find the speed that this crate has at point B after it's gone through a displacement of 2 meters. To do that first, we're going to use the work-kinetic energy theorem. The work-kinetic energy theorem says that the net external work done on some non-deformable object is equal to that object's change in kinetic energy. This is a special case of a more general principle known as conservation of energy. All right, let's apply the work-kinetic energy theorem right here. So I'll put that right here. So the net external work, which we've calculated, will be equal to this object's change in kinetic energy, which is the kinetic energy at this point minus the kinetic energy at this point. At point A, the object was at rest, so its kinetic energy is 0 because its speed was 0. So our net work will be equal to this. We can solve then for the speed at point B by taking this expression and rearranging it. I'll write that right here. We plug in 200 joules for the net work and 100 kilograms for the mass. 2 times 200 divided by 100 gives us 4. Square root of 4 is 2, so the final speed is 2. If you work out the units, you'll get meters per second. All right, we can also do this with a force-based analysis. So to do that, we could figure out the net force acting on the 100-kilogram crate, calculate the crate's acceleration, and then figure out, after that acceleration has accelerated the crate for 2 meters to the right, how fast the crate will be going at point B. So to do that, let's draw a free body diagram of the crate right here. I've got the downward gravitational force, the upward normal force, and of course the 200 Newton pulling force. The vertical component of the pulling force is less in magnitude than the downward gravitational force. Downward gravitational force has magnitude 100 kilograms times g. G is 9.8 meters per second. So this would be 980 newtons. That's a lot less than this, so the crate will not be lifted off the horizontal surface. And the only acceleration that's going to happen is to the right. So all we got to worry about is our acceleration in the x direction. And I've chosen a coordinate system, x to the right and y up. So I can break this into components. I don't even need to worry about this component here, the vertical component, because I'm not worried about the up and down. I'm just worried about the left and right. This side is adjacent to the 60-degree angle, so we have 200 newtons times the cosine of 60 degrees, which is 100 newtons. So I can write Newton's second law, x component form, right here. Looking at the sum of the forces in the x direction, I see only this one, the 100 newtons. So that's going to be equal to the mass, 100 kilograms, times a sub x. So I'll write that here. Solving for a sub x, 100 newtons divided by 100 kilograms will give me 1 meter per second per second. So the crate is accelerating to the right at 1 meter per second per second. Given the horizontal acceleration, given the horizontal displacement, I can use an appropriate equation from kinematics to figure out how fast the object's going right here. I'll put it right here. A sub x is what we just calculated. Delta x is this 2 meter displacement in the x direction. V sub x0 is the x component of the velocity at the beginning of that displacement interval, which is the velocity right here, which is 0. And v sub x is the x component of the velocity at the end of that interval, which is what we're trying to figure out. So let's take the square root of both sides, put it here, where I've plugged in for the acceleration and displacement components. And this comes out to 2 meters per second. And this agrees with our earlier result. Now I need to note a subtle point. What we calculated earlier was a speed. Speed is what appears in the kinetic energy formula. Speeds are always positive. So regardless of what direction the thing is going, you're always going to get a positive answer for speed. Whereas what we calculated here was the x component of a velocity. It could have come out positive or negative. Based on our choice of coordinate system and based on the direction this thing was moving, we got a positive result. But in theory, it could have come out negative. So you have to remember, when you're using the work-kinetic energy theorem to figure out things about motion, you don't get velocities, you get speeds. So now let's explore the what-if scenario. What if, in addition to the original pulling force, we have another pulling force of magnitude 100 newtons and direction 30 degrees above the leftward horizontal? What will happen then? Well, first, let's check to make sure this thing is still going to accelerate to the right. So we already calculated the rightward component of this 200 Newton pulling force. That was 100 newtons. This component here will be to the left, 100 newtons times the cosine of 30 degrees. That's 86.6 newtons. So this component will overcome this component, and the whole thing will accelerate to the right. All right, so now that we've verified that this thing will still accelerate to the right, let's figure out how fast it's going to be going at point B, again assuming it was still at rest at point A. And we'll use the work-kinetic energy theorem for this. So we need the net work. Well, the net work will be the sum of the work done by the 200 Newton force, which we've already calculated, and that won't change because none of the conditions in that calculation will change. We've also calculated the work done by gravity and the normal force. Those are both 0. So all we need to do now is also calculate the work done by this 100 Newton pulling force. So to do that, let's rewrite that right here using this expression. So to work out this dot product, I need the magnitude of the 100 Newton pulling force. That's 100 newtons. The magnitude of the displacement, that's 2 meters. And the cosine of the angle between the 100 Newton pulling force and the 2 meter displacement. Now we got to be careful. The displacement's this direction. The 100 Newton pulling force is in this direction. So the angle between them is this angle right here. That angle is 150 degrees because 150 degrees plus 30 degrees would give us the full 180 degrees. So the angle between the pulling force of 100 newtons and the 2 meter displacement is 150 degrees. I need to put that cosine in right here. Now, the cosine of 150 degrees is equal to the negative of the cosine of 30 degrees. Both of those things give a negative result. So I could have put in minus cosine 30 degrees instead of cosine of 150 degrees. Both of those give the same result. So you can always use the full angle between the force and the displacement, or you can choose the smaller angle, provided that if the component of the force is opposite the direction of the displacement, then you put in a minus sign by hand. All right, so we multiply this out, and we get for the work done by the 100 Newton force, negative 173.2 joules. We can understand the negative sign conceptually as follows. Imagine that the crate was already sliding to the right and that we didn't have this force here and we only had the 100 Newton pulling force up and to the left. The leftward component of this 100 Newton pulling force would be slowing the crate down. Slowing the crate down means its kinetic energy would be decreasing, so delta K would be negative. So this 100 Newton pulling force would make a negative contribution to the net work. We can now find the net external work done on the crate as it undergoes this 2 meter displacement from point A to point B. That will be 200 joules plus 0 plus 0 plus a negative 173.2 joules, and that gives us 26.8 joules for the net work. We can set that net external work equal to the change in kinetic energy. The initial kinetic energy at point A was 0, so we can again solve here and get this same formula, except now instead of plugging in 200 joules for the net work, I'm going to plug in 26.8 joules for the net work. So I can take this result, put it here, where I've plugged in the new net work and the 100 kilogram mass of the crate, and I get for the speed at point B 0.73 meters per second. So that would be the speed at point B in our what-if scenario. Before signing off, I'd like to answer the following question. Why bother developing concepts such as work and energy when we could already have solved this problem just fine using force-based methods? I'll give you two answers. First, there are mechanics problems that are more complicated than this one that are easier to solve using energy methods than force methods. Second, and this point is much more important, energy, unlike force, is applicable at all scales and across all realms of physics. For example, force is of limited use in understanding heat transfer and radiation, and the concept of force is almost entirely absent from quantum mechanics. Energy, on the other hand, is very useful in understanding heat transfer and radiation, and energy is a fundamental concept in quantum mechanics. Don't get me wrong, force is indispensable in physics, but in the big picture, energy is a much more universal and fundamental concept, and it's not even close. All right, that's all for now. Thanks for watching, and I'll see you next time.